Hi, I'm Zor. Welcome to Unizor Education. I have decided to put a little bit more information into Lagrangian chapter, especially for non-conservative systems. Before, we were talking about only conservative systems, like, for example, some kind of a object is moving in the gravitational field. Well, gravitational field is potential field. It has a function which is called potential, and the force depends on the position. But in some cases, the force depends not only on position, but also, for example, on speed. That complicates the picture. And Lagrangian, in the form which we were using it before, cannot actually be used. So today is this particular example of non-conservative system and how to build Lagrangian for this system. Okay, so this lecture is part of the course Physics Plus. It's a chapter called Lagrangian, and the lecture is called Non-Conservative Lagrangian. Now this course has prerequisites. Before Physics Plus, I had Physics for Teens, and also I have math courses, Math for Teens and Math Plus. So I presume that all these prerequisites are totally familiar with you, because I will use some concepts which I was basically introducing before. So this is just a continuation. Now the website unizor.com is totally free. There are no advertisement. You don't have to sign in, no subscription, totally free thing, pure knowledge for your consumption. Every lecture has written part, like notes, and they are written usually in the style of textbook. So you can watch the lecture in a video, you can read the corresponding text, which is on the same web page on unizor.com, and that would help you to understand material much better, obviously. So you have a textbook, and you have a video presentation of the same material, basically, on the same web page. Now there are some exams, not in this particular course, but in previous courses there are exams which you can take as many times as you want, just to self-check yourself. There are some provisions for supervised education on the website, again, totally free. Alright, so let's get back to business. Now, as I was saying, our Lagrangian we were familiar with, which typically was like L is equal to T minus U. Lagrangian, kinetic energy and potential energy. Now, kinetic energy was more or less like 1/2 mv squared, or maybe some other quadratic form. The potential energy was just a function of position. So if that is true, then, well, the Lagrangian of this type more or less fits. But now let's consider a completely different problem. Let's say you have a surface of water, and you drop a stone. Now the stone goes down the water. Why? Well, there are two different forces. The first force is obviously its weight. Now let's say we have x axis directed downwards. So there is a force which is its weight, and another force is the force of resistance of water. Now the water is such a media that the resistance actually is not constant. It depends on the speed. It's actually proportional to speed, more or less within certain kind of precision things. So I assume that the force which is actually directed against the motion is proportional to its speed. Okay, so there are two forces. And first, let's do what classical Newtonian mechanics is doing in this case. We have two forces. In this case, they're one-dimensional, so introducing Lagrangian will not actually do a lot of new things and will not be very useful. Lagrangian is good in the complex systems. This is a simple one, but it's just an example just to show how Lagrangian would be working in non-conservative case. So, simple case, we have two forces along the same line, x-axis. This is the positive direction, this is negative direction. So, the Newton's equation would be what? That the force is equal to acceleration, right? Mass times acceleration. So mass times second derivative of time. X is coordinate, so this is m and this is acceleration a. Now this is force, basically, mass times acceleration. And what is the force? The force is mg minus k first derivative. Speed is first derivative of position. So this is my second Newton's law, and it's actually rather simple differential equation, and I'm going to basically not to solve it, I'll just give you the result, because solution is completely outside of the scope of this lecture. It goes to differential equation and it's easy. So for those people who are familiar with differential equation, they can actually try to solve it. And the first step would be instead of first derivative, you can put just another function, y, which is the first derivative. So now you have the derivative only to the first degree, right? So my is equal to mg minus ky. So this is differential equation of the first order, relatively easy to solve, and I'm not going to do it, and I'm going to write immediately the result of this, just for you to know that this differential equation has an interesting result. And what is the result? X of t is equal to mg, this is g, gravitational constant, divided by kt minus m square g divided by k square if kt divided by m minus 1. Well, it's rather complex formula, but look, it satisfies basically this equation, and it satisfies x of 0 is equal to 0, and speed at the time is equal to 0. My position is on the surface, and there is no speed, so I just put it there and let it go. So this is the equation which basically corresponds to this particular condition. Oh, I think it's plus here, not minus. Yeah, so it's plus. Now if t is equal to 0, this is equal to 0, and this is 0, so it's 0. And then I can put the expressions for the first and the second derivative. mg divided by k, 1 minus e to the minus kt divided by m. And the second derivative, acceleration, is equal to g times e to the minus kt divided by m. Okay, so I'm just giving it to you as pure math thing. I'm not going to spend any time on actually solving this. or taking the derivative. It's all basically kind of elementary stuff. I'm not going to spend any time on it. But what we actually can do from it, we do some kind of a logical conclusion. Look, acceleration is always positive, although with t going to infinity, this thing goes to zero. So my acceleration, while positive, still going to zero, like reverse exponential thing. My acceleration, graph of acceleration would be like this. This is 1. At t is equal to 0. Okay, now, which means if acceleration is positive, although it just goes to 0, but it's positive, which means speed is increasing. Positive acceleration, so speed is increasing. So this is an increasing function. However, since acceleration goes to 0, my increase of the speed is also going down. And the whole thing actually, as t goes to infinity, so this is 0, it goes to maximums. Basically, it's a maximum speed. The limit, speed limit is mg divided by k. This is 1 minus, so this is 0, so it will be only mg divided by k. So this is a limit speed. Eventually, as the stone goes down in the water, it goes faster and faster and faster. However, it's not an infinite increase of the speed. The speed will increase up to this limit, not reaching this limit. So it will be faster and faster, but still. And eventually it will be from the observer after a certain amount of time, when this thing is really substantially 0, it will look like the speed is constant. So it will constant with a constant speed going down in water. So this is my basically research based on equation and its solution, and an analysis of the speed and acceleration. Fine, this is Newtonian thing. It's not very difficult at all, so there is no need like inventing Lagrangian, etc. But I'm using this as an example of using Lagrangian mechanics to get some formula for Lagrangian and Euler-Lagrange equation in this particular case, which will be definitely different from conservative system. Why? Because of this force, which depends on the speed. All right, so let's go to Lagrangian. So this is my Newtonian second law. Now, if Lagrangian exists for this system, then the Euler-Lagrange equation, which is this, no, first we go by time, right? Of partial derivative x prime t by dx prime equals to dl what x prime t by dx. So this is my Euler-Lagrange equation. So if Lagrangian to this system exists, then solution of this equation, and this equation, I mean, L is some kind of a formula which depends on x, x prime, and t. Then solution would be x of t, some kind of a function. Should be the same as solution to this thing. So these two equations must be equivalent. Now, how can I come up with this particular function L, expression which depends on x, x prime, and t? How can I come up with this in such a way that this equation is equivalent to this equation? Well, from the first glance it doesn't seem to be easy, but some smart people actually came up with a very interesting approach to this problem. Let's take this equation and try to modify it in such a way that it will look like this equation, where L is some kind of a function. So that's what I'm going to do. I'm following those smart people who have already done it for me. So first of all, we will modify this equation. We'll divide it by m. That would be easy. And instead of k, I will put k divided by m. And I will even do it better. I will put this to the left, so it will be plus, and g would be to the right. So it will be plus this equals g. So this is the same Newtonian second law. I'm just rearranging a little bit. So I will use this as my starting point, and I will try to change it in such a way that it will look like this one. Okay, so what actually was kind of an ingenious guess was, let's multiply both sides of this equation by e to the kt divided by m. So what I will have is this. I will have this. I will not use t, it's assumed basically, plus this equals this. Right? Just multiply by this multiplier, which is never equals to 0, by the way. So I did not really introduce anything new. It's equivalent equation, equivalent to this one. Whatever is the solution to this is solution to this, and vice versa. Now, look at this expression. I'm just saying that I can recognize this as the derivative by time of this function. Why? That's the product of two functions of t. This is a function of t, this is a function of t. So it's this one times derivative of this, which is this, plus this times derivative of this, which is e to the power of kt divided by m, times the exponential coefficient at exponent, it would be k over m. So this is the left part. Okay? Okay. I need this to be equal to this, right? Well, that's easy, because this is function of t, and this is partial derivative only by x prime, by the speed, right? So I can actually have dt d by dx prime of what? Now this is function of t. I can put it as is, and for having, okay, so partial derivative by x1, x prime. Now this is not related to x prime, so it's like a multiplier where partial derivative, so it's only depends on x prime, and partial and derivative of 1/2 of x prime square is obviously 2, cancel this 2 and x prime. So this is what it is. So this is my left part, and it looks very much like this. Now, what's on the right part? Well, on the right part, I have to have a partial derivative by x, but this doesn't depend on x. So basically, if I will have it as a partial derivative by x of e to the power kt divided by mg times x. Partial derivative of x would be this, right? Now, I can say that these are equal. This is equal, right? So I'm just converting this thing into slightly different format, but now it looks much better, much closer. The only problem is this is the same function, L and L. Here I have two different functions. However, what's very important, this is partial derivative by x prime, and this thing has no x prime. So I can always add this to this without changing anything. So if instead of this I will put this plus this, derivative by x prime will not change because this thing is not dependent on x prime. So I can always say that this is d by dt, d by dx prime, e to the power kt over m 1/2 x prime square plus e to the kt over m gx. That's on the left side. Now, on the right side, I have partial derivative by x. This thing doesn't really depend on x, so I can add this to this. And that would be d by dx of, again, of the same thing. Which means this same thing, this one, e to the power kt divided by m, is the same on both sides. So I can have this as 1/2 x prime square plus mgx. It can be my L of t of x x prime and t. So with this L, this particular Euler-Lagrange equation is exactly equivalent to this one, because I was just converting with absolutely equivalent transformations. No, this is not m. This is just gx. I'm sorry, m is out. All right, so this is my function, but I would like actually to be a little bit more physical, so to speak. Now, if this is function, if I will multiply it by constant both sides, it will be the same thing. So instead of this, I will put this 1/2 m and m here. This is my Lagrangian. Why did I do this? Because this looks like a t. This looks like minus u. Minus because x is going down. So as x is increasing, potential energy is decreasing, right? So what is my final formula? Used to be, remember, L is equal to t minus u for conservative system. And for this particular system, it's e to the power kt over m times t minus u. Looks like it, but there is one multiplier which depends on time. So that's what's very important. So we have come up with a Lagrangian which is kind of resembling in some way the non-conservative system, but the conservative system, but because this is a non-conservative and time-dependent, this time dependency in this particular case, this particular problem, is reflected in this multiplier, which is explicitly dependent on time. And since it explicitly depends on time, there is no such thing as conservation of energy. And there are some nice, you see, many very nice features of Lagrangian and Lagrangian mechanics are actually for conservative systems. Non-conservative systems present problems. Now, in this particular case, we have come up with certain solution which results in a very interesting kind of function, which I like that it resembles the conservative system with just one multiplier. In the more sophisticated cases, it's probably much more complex. We are not going to go. However, this is an example of using Lagrangian mechanics for a non-conservative system. So it is possible, although it loses its many of its nice features, like conservation laws and some others. So Lagrangian mechanics is nice for conservative systems, and in many cases it gives you a lot of advantages, like for instance generalized coordinates. This is not generalized coordinates, and again in some more sophisticated case it will not be possible to do like a relatively simple conversion from a Newtonian to Lagrangian mechanics. So that's what it is. I just wanted to give you this particular example. I do suggest you reading the notes for this lecture. They are a little bit more detailed, but not by much. But still, what's very important is approach. Approach is take the Newtonian second law and convert it into format which looks like Lagrangian. That's what actually was done. Kind of artificial, I agree, but well, whatever. I mean, it works. All right, so thanks very much, and good luck.